Hi, my name is Slade Meadows, and this is my final project for ADTA 5560. So for part one, or section one of the final project, we had to select a data set to use for a time series data analysis. I began my search for data sets. I went to Kaggle, which is a great site for finding data sets for data science projects and data engineering projects. I selected a house property sales time series data set. I really like this one because it was the data looked fairly clean. It was interesting, and I'd used it before for a previous assignment and a previous project for another class, and so I was kind of familiar with it. It contains 29,580 records. It's a multivariate data set, which pretty much just means that there's multiple variables that affect the price or the value we're looking to predict, other than the time and the time series. It's sales data for properties from 2007 to 2019. Like I said, I found it on Kaggle, and the link is right here. And so the data set contains 5 fields. The first field is the date sold, which is the date the property was sold, timestamp. The postcode, a 4-digit postcode. I believe all the postcodes are from around the same region, so I don't think they're much help in looking at the prices, but there may be some leeway there. From what I read, it was just for like indexing purposes. The price, which is the price the property sold for in US dollars. The property type, which is house, unit, like apartment unit, etc. And the bedrooms, which are the number of bedrooms on the property. And so the price can vary by not only the date sold, which is the time series, but also the property type and the number of bedrooms, and possibly the postcode as well. So for section 2 of the final project, we created a recurrent neural network, a simple recurrent neural network with sine wave data. And so we generated the sine wave data the same way we've done for a previous assignment. I think it was like assignment 3. And so we built a recurrent neural network. We trained it and tested it on the data. We divided the data into 1,024 data points between the range of 0 and 64. We split the data into training and testing sets, with 20% of it being testing, which was reserved for the testing phase at the end. After the data trains, it gets tested on data it has not seen. We normalized or scaled it into a range of 0 to 1. So there wouldn't be any negative values or anything like that. The length was set to 50. The length is the number of historic data points used, in the time series, the sequence of that. The batch size is set to 1, which is the number of historic data point sets being used at one interval. And so we only had to build one model for the simple RNN for section 2 of the final project, but when I went in and was running it, it was running pretty quickly, and the first one I ran I didn't really like, so I ran 3 because it was able to change them pretty quickly. And so I built and tested 3 different models, each with 2 layers. The third model, the final model, was the best. The first layer for all models is a simple RNN. For the first 2 models, it had 200 neurons. And then the second layer for all models was a dense, fully connected layer, and it had 1 neuron for all models. So the input shape for all models was 15. The number of features was 1. All models compiled using the mean squared error as the loss function. The loss function is what the network is trying to minimize for each epoch. And so the mean squared error was what it was trying to get the lowest value for as it was training. All models use the Atom as the optimizer. I trained the first model with 25 epochs. And epochs are the number of times a model will work through the training data to completion. So I'm only going to speak on the loss function for the third and final model, which was the best model, because I don't feel it's necessary to go through that for the first two models. Like I said earlier, the first model was a kind of trial and error. After I applied, the training data to them, I would use the testing data to see how they performed, and I plotted those. So here are the predictions versus the actual data for the first model. As you can see, it was not accurate at all. I'm not really sure what happened on this because I haven't seen anything like this in the similar assignments we've done. So it's just a failure on all our accounts. The only thing I guess is the high number of neurons of 200 with the high number of epochs. So obviously it was a failure on all parts. So I redesigned that and changed the number of epochs to 25 to 5 because it was the first assignment we did using the same data. We used 5, and so that got it looking back in kind of a normal range. As you can see on this one, it kind of finds like a pattern in the data. It's not getting the right pace for the sequence, but it's understanding that there's a sequence there, unlike the other one. And so I was thinking, maybe that's too many neurons, because again, the first assignment we did using this data did not have that many neurons. And so I redesigned it once more. And so for this one, here's a diagram I made for this one. I had 75 neurons in the RNN, simple RNN layer. And then again, 1 neuron for the dense layer. Was reduced from 200 to 75, and I increased the number of epochs since the dropping over 25 seemed to help, but I thought, maybe since I was dropping the neurons, the increase in epochs would help a little bit. And so I knocked the epochs to 10, left everything else the same. So the loss for this, out of the 10 epochs, you can see the numbers listed here. The higher loss means more errors. So it performed best on the 1st, 4th, and 10th, which is really low. As you can see, some of these are pretty high comparatively to the low ones. It performed worse on like some of the last 2. So the third model was fairly accurate. As you can see, it kind of lines up with the actual data. It's really accurate through here. I mean, obviously it's off, but it's following the pattern almost exactly. It starts having problems on, around 56 on the x-axis. And so after that, it kind of grows further and further apart. So it could definitely be improved, maybe by adding another layer or just, getting a better fix on the neurons and epochs. But this isn't too bad compared to the first 2. So for part 3, we just kind of discussed the core concepts of the long short-term memory neural network, which is different than the simple recurrent neural network. While this is also a recurrent neural network, it is more complex than the just simple RNN, which is considered like the vanilla model. So this LSTM was kind of created to solve the issue of the vanishing gradient. I've read a bunch of articles on it. It's hard to understand, at least for me, but the long short of it is that the vanishing gradient causes long-term memory issues with recurrent neural networks, or the basic ones. And so things that happen at the beginning of the network, it has problems, retaining that information throughout, and that kind of decays over time. And so the LSTM, it has a a memory state that preserves long-term memory as well as captures new short-term memory and kind of combines them together. And so it accomplishes this by being way more complex than the RNN. Each cell has a whole internal state that was pretty much like a neural network in itself, like a mini neural network within another neural network. So the cell state is the channel that kind of travels all the way through the recurrent neural network and the LSTMs, with each cell being like a link in a chain, and with the cell state being a chain. So relevant information is carried over from one link to the next, and irrelevant information is dropped depending on the snapshot or the cell, the particular cell. So like I said, each cell has a snapshot similar to short-term memory. Obviously, humans need both short-term and long-term memory to survive and to do complete, simple tasks like language writing, sequencing, stuff like that. And so the short-term memory that are important are stored in the cell state, which is the long-term memory. And each cell determines which new information that it gets is important, which old information can be dropped, and the combination of all that allows the LSTM to perform a lot of tasks that basic simple RNRs have issues with. And so the inner workings of these LSTMs are, there's three what they call gates. There's the forget gate, the input gate, and the output gate. And so like I said, the gates are what make it a lot more complex and have their own like activation functions and kind of their own stuff going on inside each one of these cells that make it like a mini neural network for each of the links in the chain. The first gate is the forget gate, and it determines which information is stored in the cell state long term and what information is kind of forgotten from the long-term memory. It filters the previous, so each chain, each link in the chain kind of puts forth a send to the next chain the updated cell state and the updated hidden state. And so the filter takes the previous hidden state and the new input state data. And so it takes the previous hidden state and it takes in new data from that data point. And then it uses the sigmoid activation function, which knocks everything into between 0 and 1 with no negative values. Then those output values are pointwise multiplied and then added to the previous cell state, which is like the whole chain. And so data deemed irrelevant by the forget gate will have less influence in the following steps with the next two gates. I know it's all complicated, so bear with me. Here's a little diagram of it. So right here is the previous hidden state coming in and the new input data coming in. And so here's a sigmoid activation function kind of filtering that data. And here's the previous cell state coming in, and it kind of adds that to it. And removes anything that doesn't need to be in there. And then as you can see, it goes to the next gate right here, the input gate, which we'll talk about next. So the second gate is input gate. It determines what information should be added to the cell state, which is the long-term memory. It's a single gate, but comprised of two gate components. Sorry, let's go forward. Right here, you see the two cell gates, but it is considered one gate. The first component is the new memory network, and the second component is defined as the input gate. It takes the same two inputs as the forget gate, which is the new input data and the old hidden state. So the new memory network uses a TAN activation function, which knocks everything to between -1 and 1. Unlike the sigmoid, which is between 0 and 1. The other gate, the other component of the gate, the input gate, uses the sigmoid function, which knocks everything to 0 and 1. The the filter, it filters data to determine what's important enough to store in the long-term memory. And then the output of those two components are pointwise multiplied like the forget gate. And here's the diagram again. And then we move to the final gate, which is the output gate. And so the third and final gate is known as the output gate. It defines the new hidden state used for the next iteration in the chain, the next link. And so it uses three inputs. It uses the updated cell state, the previous hidden state, and the new input data. So let's go forward once. So here it takes the new updated cell state right there, and then it takes the input data and the previous hidden state, and then runs them all through right there. And so the updated cell state above is passed through the ton function, and the previous hidden state and the new input is passed to the sigmoid function, and it does some pointwise multiplied. And then, as you can see, in the next thing, it shoots it out. And so then another version of this, pretend right here, we'll get the new hidden state, the new cell state, and then a new input data point. And so from there, you can see, how it kind of all plays out.